Hello everyone, this is the reveal training number 3. We started with the first training dedicated to medical aspects of the project. And the second one was about proteomics and analysis of genes in the cells and organoids. And the third training is about phase measurements that we do in the project. And we decided to divide this training into two parts. The first part will be presented by me now, and the second part will be presented by Cedric at the beginning of January. So let's start with some basic information. To analyze the biological cells with optical devices that we use light as the carrier of the information. So let's start by explaining what is light and what are the parameters of light. So in principle, light is an electromagnetic wave that is composed of the electric field component, which is a sine wave, propagating in the shown direction, and the perpendicular magnetic field component. And since the magnetic field component is always perpendicular to the electric field component, we never show it in the drawings. So from now on, when you see the sine wave, this will be only the electric field component, and that is because we know that the magnetic field component is always perpendicular to the electric component. So this is the light wave, and it has a one basic parameter, which is the wavelength, which is the distance between let's say two consecutive peaks in the wave. But there is also the amplitude of a wave, and that is just the maximum value that the wave has. And there is also the phase, and the phase describes the delay of the phase with respect to some arbitrarily chosen starting point. So if I now take another sine wave, this is the electric component, and shift it to right with respect to this red sine wave that you can see here, so it would go like that, then it would be shifted to the right, which means that the phase of the red wave would be delayed with respect to this new wave. So there are two types of samples that we can measure with optical devices. And one type of object is amplitude objects, the other one is phase objects. So let's first analyze the reference wave. So this will be our electric component, our wave traveling in this direction, and it does not go through any object on its way. Now let's analyze a similar wave which travels just like the reference wave, but at some point it propagates through an amplitude object. And the amplitude object is an object that does not change the phase of this wave. The phase is the same, as you can see. The peaks are still aligned. However, you can see that the amplitude of this wave decreased, and that is because this amplitude object absorbed some energy associated with this wave, and since the energy is now lower, then the amplitude also drops. Then we have the phase objects, and the phase objects do not change the amplitude, so no energy is absorbed in the sample. However, the wave is delayed with respect to this reference wave. So we can see that at the beginning the peaks were aligned, but after going through the object this wave gets delayed with respect to this wave, and this is this delay. So this phase delay, this phase retardation depends on a parameter that is called refractive index. And the refractive index is a parameter that characterizes a sample. This is the property of a sample, and it specifies the speed of light in that material. So to calculate the refractive index, you take the speed of light in vacuum and divide it by the speed of light in that material. So for example, if you have the refractive index of 2, that would mean that light propagates twice as slow in this material as it would in vacuum. So usually the refractive index value ranges for example for the glass in the range of 1.5. For biological cells it is around 1.3, 1.4, depending on the substructure of a biological cell. Different substructures of a cell have different refractive indices. So if you put a camera here, like a normal CCD or CMOS detector, what you would notice is that the camera can see the difference between this wave and this wave, because the camera can detect changes in the amplitude. However, it would not see any difference between this wave, the reference wave, and this wave, which has the same amplitude but is delayed in phase. There would be no difference between these two waves. The camera cannot detect changes in phase. So since we are interested very much in analysis of the phase, because it carries information about the refractive index, then we need to find out a different method of analyzing the phase, and this is what this presentation is about. So the biological cells in principle are amplitude phase objects, which means that they are a little bit amplitude objects, so they absorb a little bit of energy, but they are also, of course, phase objects, so they introduce phase delay. So up to now I was describing a single sine wave. In microscopy we don't work with single waves. We work with the whole light beams that consists of multiple waves. So let's create more waves, and let's align them so that the peaks are let's distribute these waves so that the peaks are aligned. So now if we connect the peaks of each wave with each other, we will create a surface, a line. And because we distributed the waves so that the peaks are aligned, then of course we will create straight lines. So these lines are called wavefronts, and usually when we draw some optical microscopy, when you'll see optical microscopy pictures, and you will notice that we usually don't draw these sine waves, we only leave the wavefronts. It makes it easier to talk about the light beam. So in that case, this wavefront is called the plane wave, because this wavefront is planar. But of course, if we distribute these sine waves differently, then we could create another very characteristic wavefront, which is called the spherical wavefront. But let's focus right now on these plane wavefronts, so the plane waves, because we will use them in this presentation. So just to conclude this part, if we have an incident light that propagates to the right, and we have a specimen which is a phase specimen, purely phase specimen, then it will create a delay in phase in this propagating light. So you can see that this light that went through the sample is now delayed with respect to the light that did not go through the sample. And this delay, this distance, is what we are interested in. So let's now imagine that we have a biological sample or any phase sample, and we have a plane wave which falls on this sample. So on the other side, when this plane wave propagates through this sample, we get a distorted wavefront, and this wavefront looks like this due to a phenomenon called diffraction. And the diffraction is something that makes measurements with visible light different, for example, from measurements with X-ray imaging. In the X-rays, we usually assume that the planar wavelength, plane wave is still a plane wave. When it passes through the sample, only the amplitude changes according to some structure in the sample. When we make measurements with visible light or near infrared light, we observe that the wavefront is diffracted. It's distorted. It is no longer a plane, a set of planes. So this distortion carries information about the structure of this sample. So if we put a microscope objective here to see, to gather this light and put it onto the detector, then you will notice at the camera that you see almost nothing. So this is of course not entirely true, because you will see something, and you will see probably some boundaries of the samples, maybe some gradient of in the structure, but the contrast will be very low, and the values of the pixels will mean nothing, and I will explain it in a moment again. So how can we retrieve the information about this distortion of the plane wave? So what we do is we put we generate another plane wave which falls directly on the detector without going through the sample. So we know the parameters of this wave. We know that it's a plane wave, and when it falls on the detector, it interferes with this wave. So actually this is this wave that went through the microscope objective. So this plane wave interferes with this object wave at the camera plane, and as a result it creates fringes at the detector. So you will immediately see fringes, and when you look closely at these fringes, you will see that these are cosine fringes. So in this direction it is like a cosine function. So if there is no sample in the field of view, then the fringes will be straight fringes, straight lines. If there is a sample in the field of view, and I have simulated here a spherical object, then you will see that the fringes deviate from straight lines. They bend where the object is. And this deviation of the fringes from straight lines carries information about the phase of light that went through this sample. So this is how the fringes look like in the ideal case when there is no noise, but in practice, of course, we have noise in the system, so the fringes would probably look more like this, but it's still the simulation. So let's now look at the real real example. So this is the bright field image of a biological cell, and as I said, you see something. You can see some gradient structures. You can see basically the structure of the cell. However, not everywhere. For example, in this region it disappears. It is transparent. So there are regions where you see nothing. So this is one thing. The other one is that the contrast is poor. And the third one is that if you analyze the values of the pixels in this image, they carry no useful information. These values mean nothing. So this is the bright field image. So let's now add another. Let's now put this wave additionally onto the detector. So now you can see that the fringes appeared, and the fringes are very dense, so they are not visible with the naked eye here, but if you look closely, if we zoom in to this region, for example, you will see these fringes here. And these are the same cosine fringes, so if you take the cross-section in this direction, you will see this very dense cosine function. And maybe it is not very clearly seen here, but you can trust me that these fringes deviate from straight lines whenever there is some structure, some cellular structure. So for example, at this boundary right here, they do deviate from straight lines. So how can we extract this information about the deviation? We calculate the Fourier transform of this image, and this is the result. This is the spectrum of this image. This carries information about the frequency components in this image. And because we have this straight, these fringes here, our spectral information is divided into three parts: the central part and two parts. One here and the second one here. So we have three parts. The central one is not interesting for us. It carries no valuable information. What we are interested in is this information in the corner. And it doesn't really matter if you choose this information or this information. It's in principle, this is the same information. So this region here carries all information about our analyzed sample. So we select this region, we remove the rest, so we clear the rest, we move this information to the center of our spectrum, and we calculate the inverse Fourier transform. So this is the result of the inverse Fourier transform. So if I now would click and show you the values of pixels in this image, then these values would already carry information about the phase of light that went through the sample. However, you can immediately see that there is something wrong with this image. You can see that there are these discontinuities here. This distribution is not continuous. There are these jumps here, and these jumps are due to phase wrapping. And this is something that there is nothing we can do with the phase wrapping. It will always be present when we calculate the inverse Fourier transform. And and the phase wrapping is in principle, this is the wrapping of the values with the modulo 2 pi function. So if you have a distribution like this and the values go up to 16 pi, then the wrapped phase will look like this. It will go up until it reaches 2 pi, and then it gets wrapped. It starts from 0 and it starts again and again and again and again. So what we do with this distribution is we apply some phase unwrapping algorithms, and there are many different phase unwrapping methods. This is not really important right now, how these methods operate. But basically what they do is they move this section up so that this distribution becomes continuous, and then they take the bigger region, they move it up even more so that it becomes continuous with the next fragment, and so on and so on. It modifies this image as long as you get the continuous distribution. So after applying the phase and unwrapping, this is the unwrapped phase that you obtain. So what you can see here is that we have information about the cellular structures here, and no longer there is no region that would be invisible for us associated with this biological cell. And what is even more important is that if you read the value of this image, it will have the value will represent the delay of the phase according to the scale which is shown here. If we knew what is the sample thickness, so let's assume that the sample thickness in this case was 10 microns, so the cell was 10 microns thick. If we knew what is the wavelength of the light, of the laser light that we use to illuminate our sample, and we know it because we know what kind of laser we used, and if we knew what is the pixel value, and we know it because we have just retrieved this information, then we could calculate what is the difference between the what is the refractive index difference between any 2 points in this image. So we cannot calculate the absolute value of this refractive index, but we can calculate what is the difference between the refractive index between any 2 points in this image. So if we can do it between any 2 points in this image, so we can calculate what is the refractive index difference between the cell, any point of the cell, and for example the immersion medium that surrounds the cells. And since we know what is the immersion liquid and what is its refractive index, then we can easily calculate the refractive index of the cell. So this solution has this serious drawback that you need to know the thickness of your sample to get information about the refractive index. This is in practice quite difficult to obtain. You would have to know this information with a very high precision. So this is one drawback. The other one is we only get information about the integrated phase. So it is like the X-ray. So for example, if you take the X-ray of your chest, then if there are different structures one behind another on the path of the X-ray beam, then they will be integrated. You will see them all cast on top of each other. And we have similar thing here. So if, for example, behind this cellular structure there was another structure, we wouldn't know. We would only get information about the integrated phase. So this is integrated phase, or in other words, we could only retrieve information about the average refractive index along one direction, about the direction of the beam propagation. But still, this two-dimensional phase retrieval is very useful, because what we usually do is we don't try to retrieve the information about the refractive index. Instead, we try to we can directly translate this unwrapped phase, as you can see here, into dry mass distribution. So to calculate the dry mass of cells, you can apply this very simple equation, and the m is the dry mass of a cell. The S is the area of the cell. You can read it from the image. This component, this is the average phase within a cell area, so it is also quite easy to calculate. You just take all the values here of the phase and you calculate what is the average of this value within this cell. And this alpha here, this is a constant called refractive index increment. And that is a value, it is a constant value, but you have to pick it before this calculation. And this is the value that associates the phase delay with the dry mass distribution. And this quantity, this refractive index increment, is described, you take it from tables, it is described for different substances. So for example, from lipid droplets you have a different refractive index increment. For proteins you have a different one, and so on and so on. But what we usually do is we take this value, for example, we usually use 0.18 value as the average for eukaryotic cells. And if you apply this equation, you can easily retrieve information about the dry mass of the cells that you imaged. So this is very useful solution. So what I described right now is the basis for holographic microscopy. So this is the first technique that I described today. This is the 2D technique. You only get information, the two-dimensional information about your sample. And to perform this measurement, you use this holographic microscope system that you can see here. And without going into much detail, you have a laser light, which then is split by this cube. This is called the beam splitter. So it splits the beam onto two paths. So the first path goes through the sample, through the microscope objective and onto the CCD camera. The other one is the reference arm, and it does not go through the sample. This is our plane wave that will fall on the CCD camera without going through the sample, and it is used to generate these fringes at the CCD camera. So the resolution of this system depends on the numerical aperture of the microscope objective. So if you choose the microscope objective with high numerical aperture, that means you will have high resolution in your image. The resolution, of course, also depends on the wavelength. So the shorter the wavelength, the better the resolution. However, on the other hand, when you think about a field of view in your system, it depends on the magnification. So if you choose a microscope objective with high magnification, it means you will have low field of view. So to have a high field of view, you need to choose the objective with low magnification. Unfortunately, most of the microscope objectives with low magnification also have low numerical aperture. So if you want to have high numerical aperture, probably you will also have high magnification. So that means that there is always this trade-off between the resolution and the field of view. You can either have high resolution or high field of view. You cannot directly have both with this kind of setup. So what you can do to deal with this problem is you can either choose a microscope objective that has high numerical aperture and relatively low magnification. There are such microscope objectives. These are very expensive, but there are such microscope objectives. Or the other solution, and this is what we do in our systems, is you can use a high numerical aperture objective capture one image and then use a motorized stage on which you put your sample, and you move your motorized stage and capture another image, then you move your motorized stage, you capture another image, and so on. You capture a big field of view with high resolution in each sub-image. So this is how the holographic microscope that we have looks like. So it is not scary. We just took a normal Olympus microscope, we opened it, we removed the elements that were inside, and we have put our own optical elements. So as you can see, this microscope looks much like a standard microscope. The size is the same. And this is the example of one measurement. So on the left side you can see the high field of view image. It is composed of multiple small field of view images with high numerical aperture. So we have high resolution, as you can see in the zoomed in image. We can see the substructures. This is the cell nucleus, and these are cell nuclei. And on the right side you can see the possibility of capturing time-lapse measurements. So we can put the microscope into the incubator, and we can perform long-term observations. So each frame, as you can see here, carries information about the phase. This is not the bright field image, this is the phase. So we can, at any point, we can read the values of the dry mass in each of these points here. So these measurements here are quantitative, which means that you can read the values, and the values carry information about the phase. These are label-free. Note that we do not use any staining in these images, and it is because you don't use any fluorescent staining, which is toxic for the cells. You can perform long-term observation. So what you can do with holographic microscopy systems, images, you can perform a lot of statistical analysis. So these are just two examples of what we did. Without going into detail, for example, you can analyze what is the relation between the area of the nucleoplasm and the dry mass of the nucleoplasm in multiple cells in the field of view. You can do the same with the nucleolus. You can compare the area with the dry mass, and you can do it in the time-lapse measurements, so you can analyze how this changes with time. This is another analysis that we did. It's a publication that it's a paper that we did, that we will publish, I hope, soon. We are answering the reviews right now. So what we did here is we analyzed biological cells that underwent irradiation with light with very specific dosage of energy. So this is called biochemical interaction between light and tissue. So we analyzed how the cells will behave when they undergo irradiation with light, when compared to the cells that do not undergo any irradiation with the control group. And we analyzed the statistics with time. So for example, here we can see how the mean dry mass density of cells changed. So we can see that if the cells were not irradiated, then the peak, the local peak of the mean dry mass density was in this position, whereas when the cells were irradiated, this peak moves to the right, and the higher the dosage, the bigger the delay of this peak. Very interesting results, and so we can do a lot of such stuff with holographic microscopy. So to conclude this part, we have a lot of different modalities, different types of microscopes that are used to analyze samples. So we have the bright field microscopy, but it has a very low contrast. It usually requires staining to see some details in the samples. We have phase contrast microscopy, but it shows more, but this is only qualitative information, not quantitative information, which means that the values at this image, they carry no useful information. There is interference microscopy, the DIC, but this is the same. This is only qualitative information. This is only visualization of the face, not the measurement of the face. We have fluorescence microscopy, which of course has the staining, and there is this phototoxicity, photobleaching. So when compared to these techniques, the holographic microscopy offers a lot. It offers quantitative measurement and label-free, without any staining. So to conclude this holographic microscopy part, some time ago we were asked to identify dermal fillers in biological human tissue. So there were patients who were given some dermal fillers, and dermal fillers are the substances that you get injected under the skin to remove wrinkles. And after some time, some of the patients had some problems with skin, and they didn't know which dermal filler they were given. So we were given this task. So we took 3 histological slices from 3 patients that had different fillers. And as you can see, when you compare these fillers with bright field microscopy, there is you cannot identify which filler is which, because they all are just gray structures in these images. However, when you analyze these images with holographic microscopy, you can read the value of the refractive index of the filler in each of the histological slices, and you can compare it with the non-refractive index of the filler. And based on this, we identified that here there was silicone, there was dermalife, and here was some filler called W3. So now let's move on to holographic tomography, no longer microscopy, but tomography. This is a technique that moves from 2D to 3D. And it's called holographic tomography, but sometimes it's also called optical diffraction tomography, and it's the same, so don't get confused. So holographic tomography is like CT scan, the computed tomography that you can get at the hospital. So in principle, we have our object that we are interested in, and we capture a set of projections from different angles. What we do is we don't use X-rays, we use light, and we don't measure the whole people, but we analyze the microstructures, transparent phase microstructures like biological cells. So the difference between the holographic microscopy that I have just described and holographic tomography is the same as between the X-ray imaging and CT scan. So the X-ray image is like integrated information. This is just one image, and the CT scan collects a series of such X-ray images and applies some reconstruction algorithms to retrieve information about the 3D structure. So holographic tomography gives information, the full quantitative 3D information about the refractive index and about the 3D geometry of the sample analyzed, and of course on its organelles. So it's possible to perform sectioning, And what is very important, you don't need to know the thickness of the sample before the measurement. You can just put the sample under the holographic tomography and you will retrieve the full 3D information. You will actually see your object in 3D. You can look inside, you can cut it in any direction you want. So how we perform the measurements? So let's imagine that this object in the center is our specimen that we measure. So we capture a series of projections at different angles. Each of this projection that is symbolically marked here with these lines can be performed with holographic microscopy that I described before. So for each such projection, so for each such measurement, you obtain one two-dimensional image, two-dimensional phase image. And you process these images because you will have the same dense fringes, the straight fringes in these images. So you perform the processing of these images just like I described in holographic microscopy. You obtain the two-dimensional phase distributions, the integrated phase, and you apply some tomographic reconstruction algorithms to obtain the information about the 3D tomographic reconstruction. So there are two approaches to capturing the projections. The first one is rotation of the sample. So there is your CCD camera, there is microscope objective, and there is your sample. You capture one measurement, so you illuminate your sample with a plane wave in this direction. Then you rotate your object a little bit, you repeat the measurement, and so on until you captured all the projections. And the second approach is that the sample is stationary, it is not moving, but instead you change the direction of the illumination. The advantage of this solution is that you don't have to move your sample, and that is very important when you analyze biological samples, because they when you start if you would start rotating the samples like in this approach, then very quickly your biological cells would start moving in the, for example, Petri dish in which you make the measurements, and you would spoil the measurement. The drawback is that you cannot capture measurements from all projections, from all directions. So for example, you cannot perform measurement from this direction or this direction. You can only perform the measurement from this limited range of angles. Still, however, this is the method of choice for majority of holographic tomography solutions on the market. So what we do with the measurements? So let's imagine that we have the plane wave here which illuminates our object. Let's now forget about all this microscope objectives of this optical setup that is here. This is just a symbolic drawing. So we have a plane wave which illuminates our sample from this direction, and of course we have a reference wave which creates the interference fringes at the camera and so on and so on. But as a result, after the processing of this image, you get a two-dimensional phase distribution. So then we calculate the Fourier transform of this two-dimensional phase distribution, and we cast this information, we put this information in the very specific place in the empty spectrum. So this is the spectrum. At first it is empty, but we take this data, we calculate its Fourier transform, and we put it in a very specific place on a very specific arc in this empty spectrum. Then we illuminate the sample from a different angle, let's say this one here. We capture another image, we calculate its Fourier transform, and we put the data on a different arc. And after we capture all the projections, you can see that the spectrum will get partially filled according to the picture shown here. So what you can see here is that the spectrum is partially filled. However, in this direction, and this is the direction of the optical axis, in this direction we have no information. This red information marked here is not present in this direction. And this is maybe better seen if you analyze the how this drawing looks like in 3D. It has like this donut shape. So you have a lot of information in this direction, in X and Y directions, but in the Z direction there is nothing. And that means that you will have distortion in the calculated reconstruction, but I will show it in a second on the next slide. When you fill your spectrum, the next step is to calculate the inverse Fourier transform of this matrix here. And as a result, you get your 3D tomographic reconstruction that carries information about your biological sample in 3 dimensions. And the algorithm, this method that I described here, is called the direct inversion algorithm. So this is the most simple, the most basic method in holographic tomography processing, but it is very popular. So to understand what happens with the reconstruction when you don't have your spectrum fully filled, let's compare these two cases. The first one is the spectrum of your reconstruction is fully filled, all the information is present. So when you calculate the inverse Fourier transform, you get your reconstruction with a very nice quality. On the other hand, if a part of your spectrum is empty, so there is no information in this direction, then when you calculate the inverse Fourier transform, you can see that in this direction you have no sharp boundaries, the image is distorted, the refractive index values are underestimated, so we get a lot of problems with such case. And this is the case that we have to deal with our measurements. So that hopefully explains you why when we show you sometimes the reconstructions, the 3D reconstruction that we have, then in one direction they look much worse than in the other direction. So this is the schematic of a simple tomographic holographic tomography system. So we have a laser. It is split into 2 arms. The first arm is a reference arm that goes directly onto the camera. The other one is reflects from this mirror. From this mirror goes through the sample here and then goes to the camera. So basically this system here could be the holographic microscopy system, not tomography system, just as it is shown here. However, what makes it a holographic tomography system is this element here. This is the motorized mirror. So when we rotate this mirror, just as you can see here, as a result, you illuminate your sample, which is at this plane, from different angles. So if I start to rotate this mirror, then this beam that goes here, it will start to illuminate the sample from different angles, and each such angle, for each such angle we capture one measurement at the camera. And then we process the data and obtain the 3D refractive index distribution. So this is the example of one reconstruction. So this is our laboratory setup that we use to make measurements. This is one of our setups, and I show you not to scary makes the holographic tomography scary to you, But to show you that holographic tomography is in principle a more complicated technique than holographic microscopy system. So this is one example of the reconstruction. We analyzed polymer microspheres that are 20 microns in diameter. So we can see that we can reconstruct the 3D geometry, but as well we can see any cross-section. We can look at the cross-sections in any direction, and we can read the refractive index values inside the sample. So this is our second setup, our second holographic tomography setup. So we enclosed this system, we rebuilt it and enclosed it into this casing, so it is no longer so scary. It is the size of a slightly bigger microscope, so it's not that big. However, it is quite heavy. This element here is the motorized stage that we use to to capture information in a wide field of view. So this is another example of reconstructions. What you see here is the cross-section, two-dimensional cross-section through three-dimensional tomographic reconstruction. So this is no longer like we had with holographic microscopy, where we only had access to 2D integrated information. What you see here is the 2D cross-section through 3D information. So we can see that the contrast of in this image is very high. So we can easily see the nucleolus, which is here. The mitochondrial network is seen here. The cell nucleus, which is this one, and here the same information shown with different cells. And here are a few more examples of some biological cells that we analyzed with our setup. So there are some individual biological cells, but also we analyzed red blood cells. It was whole blood sample, and this is the blood sample of Arkadiusz. Actually, he took his own blood and measured it with tomography setup. So we can see that we have access to three-dimensional geometry of each red blood cell, but not only. We could see into any cross-section in this image and read the values of the refractive index here. This refractive index can be easily translated into dry mass distribution, but this time this is the 3D distribution of the dry mass. And here is the example of a measurement that we performed with some histological slice. And this is again the cross-section, two-dimensional cross-section through this three-dimensional reconstruction of this histological slice. And finally, this is the last reconstruction that I wanted to show. This is the biological cell that undergoes some process, and this is to show you that we can create something that I would call digital staining. So we can give different colors based on the refractive index values. So you can see that we have the cytoplasm, which is red, and we can see the different substructures in this biological cell based on the refractive index distribution. Okay, so thank you very much, and at the beginning of the January we will continue this training, and the presentation will be given by Cedric. Thank you.